Now we understand the basic difference between not difference. Now we just understand what is SA node, right? SA node, that is sinoatrial node, right? Let's try to understand the ventricular myocyte contraction, right? So what happens here is that there are multiple phases here: phase 0, phase 1, phase 2, phase 3, and then phase 4. So we have 4 phases, and as you can see, 0, 1, 2, 3, and 4, they are in number, right? So this is not a restless membrane, right? This is not a restless membrane potential. It is a resting membrane potential. It means it rests, it waits, for this impulse that is coming from SA node, right? And it waits for it. So once SA node fires this impulse, right, it spreads through the ventricles after a short delay, and this delay is done by AV node, and the ventricle cells respond very fast in very powerful way, and they have to respond in a very powerful way because the more powerful it is, the more strength it is, the more ionotrophic it is. So that's why I've written here ionotrophy. So that's the word. Ionotrophy means contractility strength, how strong the contraction of ventricle is. So that is ionotrophy. So the resting membrane is around minus 90 millivolt. So usually the cells, they rest at around minus 90 millivolt, and they have to get depolarized. Once they get depolarized, they show a contraction, and that contraction is called systole. I am so sorry. And this, this contraction is known as systole, and this relaxation is called as diastole, right? So let's talk about these phases: phase 0, phase 1, phase 2, and then phase 3, right? So the main phases are these phases, right? So the key concept here, the most important thing in all of this here is that the plateau, this is the plateau right here, and this is phase 2, right? The plateau phase 2 gives the time for the full contraction, and it prevents tetany, okay? So that's why we have a plateau. Let's study this, why it's happening. So for the ventricle, what happens here is that, so this is phase 4, right? This is pre-potential, right? This happens. So here, as you can see, phase 4 is this, right? And in phase 4, the starting point is this, okay? Understand this. The starting point is not phase 0. The starting point is phase 4. Phase 4 is the resting membrane potential. This phase 4 is responsible for giving ventricular cells a resting membrane potential, a resting state. So I told you cells have to, push out a lot of positively charged potassium. So there we have sodium potassium pumps. Now these are pumps. They stabilize the resting membrane potential until the next stimulus. So this is how the cell is resting now, right now. Okay, just imagine cell is resting, and suddenly a stimulus comes from behind. That is, SA node produces a stimulus, and this stimulus is delayed at AV node. Now, once the stimulus is delayed at AV node, it waits there for around 0.1 second, and this time is enough for this resting, right? So this stimulus passes through AV node and reaches these Purkinje cells, Purkinje fibers. Once this Purkinje fibers receives this stimulus, the phase 4 now transforms into phase 0. So phase 4 was just resting place where the cell was actively pushing out potassium out of the body, out of its cell membrane, right? So potassium out stabilizes the resting potential at minus 90 millivolt, right? And now the starting has begun. This phase 4 has begun. Once the stimulus hits these cells, the phase 0 starts. In phase 0, the sodium, that is Na, sodium, via fast sodium channels, that is phase 0, they come inside the cell. Once they come inside, the resting membrane potential from 90 jumps to maybe at minus 60. Okay, now this is not true. It doesn't jump from minus 90 to minus 60. I'm just giving an idea how it can happen. It will provide a positive charge, right? So this is what happened. So rapid depolarization happens right here. As you can see, the graph is going upright, right? So it means the amount of sodium that was pushed inside the cell was insane. A lot of sodium was pushed inside. This is the reason the graph is straight. If this amount of sodium was a little less, then the graph would be like that, right? Or if the amount of sodium was very, very, very less, then the graph would have been like that, or maybe like that. But the graph is a very straight line. It means the amount of sodium that was pushed inside the cell was insane. A lot of sodium. So a lot of sodium, what does a lot of sodium do? What happens? A lot of sodium changes the resting membrane potential from minus 90 to dipolar state, right here, dipolar state. And it changes, it jumps because the amount is a lot, right? So it jumps, and then this phase 0 overs, and now the cell is really depolarized. Now, once the cell is depolarized, right, this is phase 1. It depends upon transient potassium channels. Now, these are transient. It means they are for short-lived. They are short-lived. They are for short time. So phase 0 is that the potassium is pushed outside the cell. Now, so this is the moment when we got depolarization, right? So here we got depolarization, right? And just, it's a quick depolarization happened, right? And it's an upstroke. And after this, these potassium channels, these transient potassium channels in the cell, they open up. Once they open, a lot of potassium is lost out of the cell. Once the potassium is out, there's a brief repolarization state. Now, this brief repolarization is called early repolarization, okay? And this is a short-lived repolarization. This is the short-lived because of these transient potassium channel. Why this is short-lived? Because we use transient potassium channels. I hope it makes sense to you. There was a fast Na channels here. These are transient. These are small time. So they open up for a small time. A small amount of potassium is leaked out of the cell. Once this small amount of potassium is leaked out, the cell, the polarity of the cell, it goes back to 90. It doesn't go back to 90. It just moves towards 90 a little bit. So this is why we have this slope, or we can call it a notch, right? Here, as you can see, this is a notch, right? So phase 1 is over now. So after phase 1 is over, we have phase 2. Now, phase 1 is over. Phase 2 is that in phase 2, we have two channels. We have calcium and we have potassium. So potassium is kicked out of the cell. This is the one part. And so this calcium is pushed inside. So as you can see, we have this balance of these two ions, two positively charged ions. So these charged ions, they are, calcium is pushed inside and potassium is kicked outside. So now we have this equilibrium being made right now. So this is the reason we have this plateau. So as you can see, this is, we are literally just, being on the same RMP, okay? Because here, as you can see, this is minus 90. Here, you can see this is depolarization, dipolar state. Here, and here is minus 90, and here is a little bit repolar state. So the cell stays at this repolar state for quite long time. And why this cell stays here? Because we have two channels. L-type. L-type means long type, not transient. Opposite of transient is long type. So potassium goes out of the cell in a long type calcium channel, and it stays out. The calcium comes in and the potassium stays out, right? So the plateau phase is the time it takes for the ventricles to, produce contraction, okay? So the contraction is done by actin, myosin interaction. And as you can remember, this actin-myosin interaction is done via calcium induced, right? This actin-myosin interaction is done via calcium, okay? So once the calcium comes inside, the contraction starts, and the contraction stays for this whole time, this whole plateau time, okay? Once the contractions get over, now it's time to get, relax. now it's time to relax, because the cell has now contracted. It has pushed all of the blood outside of the ventricles now, right? And now the ventricles are empty. Now the time of filling is again, right? It's gonna happen again. So the cells of ventricles have to relax again. So phase 3 is that, again, the potassium is going out in phase 3. This is phase 3. As you can see, there is a sudden drop from this repolar state to a very repolar, very, very, very electrically negative state. It jumps from, maybe this state to this state right away. So what this straight line means, this is not an upstroke. This is opposite of upstroke, maybe a downstroke we can call it. So this is a downstroke happening. So what's happening here? So here we have these potassium delayed rectifier channels, right? So what happens in these channels? They are delayed. It means they stay for a long time. Now we need these delayed channels because we want the cell to really relax, go into this diastole. So going into this diastole, we call this Lucy. I hope you remember that. Lucitrophy, relaxing ability of the ventricles. So we want these ventricles to relax for a long time so that the blood can be filled again in these ventricles, right? So that's why the phase 3 is mediated via these delayed rectifier potassium channels. Now we are pushing out the potassium channels so that the cell can become negatively charged again, right? So this was phase 3. Now the cell has returned to its resting membrane potential, that is minus negative millivolt. Again, the phase 4 starts. Now the phase 4 starts with the help of the stimulus that was generated by SA node. So SA node, again with the help of phase 4, phase 0, phase 3, creates this, this impulse, right? And here the SA node is moving like this, from minus 60 to minus 40. Again, it goes back to 60, then it goes 40. So this is a restless membrane potential, right? So this generates this impulse. It travels to AV node. It stays at AV node for some time so that this phase of, this phase 3 can be, done. So this phase 3 can be done, right? And once phase 3 is done, the impulse comes and it activates phase 4. Now the phase 4 is this resting, state where the cell is actively pushing out, potassium, right? And potassium is going out. And usually, I just want you guys to remember that cells, wait, let me write it again. Cells are these bags of sodium that are surrounded in an ocean of potassium. This is the idea. So usually cells wanna potassium. I think I have said it maybe opposite. I'm trying to say is that cells are these bags of potassium. So potassium is inside a lot, and this ocean of sodium, right? Okay, so ocean of sodium, right? What really here I mean that in cytoplasm we have high potassium values around 140, right? And the cytoplasm has low Na, right? And there are a lot of negative charge protein inside the cells. Okay, so that's why we call the bag. That's why we call the cell a bag of potassium, because cells have a lot of potassium they want to push out to maintain this electronegativity. Okay, so that's why I call cells a bag of potassium, or maybe I said cells are bag of sodium. I'm so sorry. So cells are bag of potassium. Okay, this is potassium. Okay, so outside the cell usually there are high levels of sodium. The extracellular space is like seawater, okay, high in sodium and low in potassium. Again, sodium is around 140 as well in the ocean. The extracellular fluid, the level of sodium is around 140 or maybe 145, I don't remember, like that. So okay, so this is done, right? The ventricular action potential is done. Okay, So let's talk about these early depolarization, this early repolarization, resting membrane potential. Okay, so resting membrane potential is done via this phase 4, right? Where these cells are actively pushing out the potassium out to maintain this negatively charged resting potential, that is minus 90 millivolt. That's the idea here, right? Early repolarization. So here what happened here is that in ventricles, that's the in ventricles, the calcium influx, that is phase 2, this is phase 2, starts the calcium induced calcium released from sarcoplasmic reticulum for the ionotrophy. So ionotrophy, what is ionotrophy? Ionotrophy is contraction, and contraction is done via actin myosin, right? So this actin myosin is done via the calcium, and this calcium comes from sarcoplasmic reticulum, right? SER. So this SER is like a bank of calcium, and this SER leaks, this SER provides calcium only when it senses that we have some extracellular calcium present in the cytoplasm. So this is a calcium induced, calcium released, from sarcoplasmic reticulum, actin myosin interaction, and that gives us positive ionotrophy. So that's what I'm writing here, right? Okay, what I've written here is that we have this phase 3, right? We have this SA node. We know that SA node has phase 4, right? In phase 4, we have 3 things. Transient means slow, fast calcium channel. It comes in, changes the positivity, changes the negativity from minus 60 to minus 40, plus 20 is added. With these 3 things: funny current, and fast calcium channels, and these efflux of potassium, right? So this is done to change the electric negativity of the cell, of these SA nodal cells. And once this happens, we reach phase 0. In phase 0, there is a big calcium, influx, right? Because calcium comes in for a long lasting time, and then we have this jump, and then we get, depolarized again. Repolarization happened in phase 3. Okay, so repolarization, right? If repolarization is prolonged, how will it happen? So let me tell you about, how it really happens. So the repolarization in the SA, cells, SA nodal cells, it happens via these potassium, right? It happens via these potassium is pushed out of the cell, right? So actively we are pushing out potassium, right? We are pushing out. So imagine we have some problem in these potassium channels. If we have some problem in these potassium channels, the repolarization, the whole phase 3 will be elongated, right? Now, instead of this, the graph will come as this, because the time taken will be more. So if the repolarization is prolonged, which is seen in hypokalemia, right? If we have less levels of potassium in the cells, right? If we have less levels of potassium in the cells, then we will not be able to, push a lot of potassium out, because we don't have a lot of potassium. So in hypokalemia, this phase 3 is elongated. So SA node generates less amount of impulses in hypokalemia, okay? So QT is prolonged, and so we have this. So in ECG, we have this PQRST, right? This QT, this whole thing. So QR is the contraction itself, and T is the repolarization, right? This PQRST is the repolarization, right? So this Q to T distance, this repolarization distance, will be really prolonged. It's a long time. So this is why it is prolonged, because of the hypokalemia. I hope we know that now. Okay, very easy topic. So that was ventricular action potential right there. Now let's talk about funny currents, right? Now, why are they named funny currents? What is wrong with them? Why are they funny? So funny currents are produced by hyperpolarized. Hyperpolarized means really negatively charged. For example, I can call this minus 60 as hyperpolarized, but if it was 0, then it's not hyperpolarized. I can call minus 90 as hyperpolarized, but this is not, at 0 is not hyperpolarized. It's not even polarized. If it was plus 80, then I can also call it hyperpolarized. So hyperpolarized is just the anything which is polarized hyperly, right? A lot of polarization. So hyperpolarized, a lot of negative charged. Cyclic means cyclic. Nucleotide channels, right? Now, this is one of the most fascinating ion channels in the heart and in the eyes and in the brain, and usually people skip it. And let's break down. The full name is the full name is hyperpolarized, right? Now let me break these word word by word. So hyperpolarization activated. Hyperpolarized means they are hyperpolarization activated. So most channels like sodium or calcium, they open when the membrane becomes depolarized, less negative, okay? But on the other hand, on the contrary, these HCN channels, they are weird. They open when the cell becomes more negatively charged than usual, that is hyperpolarized. In SA node, when the membrane potential dips around minus 60 millivolts, these channels open. And this is why they are called funny currents, right? So because they behave in an opposite way to most other channels, okay? So opens at membrane at hyperpolarized around minus 60 or minus 50. So it's ironical, it's funny, because they open on a depressed state, not in a depolar state, and that's why they are funny. Other part of this name is that they have cyclic nucleotide channels name, right? They are cyclic nucleotide gated. What really means, what does it suggest? It suggests that these modulated means controlled by cyclic nucleotide. Now, what are cyclic nucleotide? Cyclic nucleotides are these CAMP and CGMP. CAMP and CGMP. Here the C is cyclic, right? So we can increase the levels of the CAMP and we can increase the levels of CGMP or decrease the CGMP. So what happened here is that in sympathetic system, right? So sympathetic system is the state of being stress, and parasympathetic is the state of being digestion, when you digest your food. So what really happens here is that the sympathetic system, it gets activated. Once it gets activated, both epinephrine and norepinephrine, which are produced locally and by adrenal gland, they are produced, right? And they go and they act on these receptors that are present on the cardiac cells, on the SA nodal cells. And then when they act on this SA node, AV node, and ventricles, right? Ventricles are very less number of these cells, these receptors for epinephrine and norepinephrine. So once they act, what happens is that they have these epinephrine and norepinephrine are binded with these G. S means stimulatory right here. So GS coupled proteins, and when they bind, they increase the levels of adenyl cyclase. Once the level of adenyl cyclase increases, we have higher levels of CAMP. Now, I told you these CAMP are called cyclic nucleotide. Okay, so once the CAMP increases in the SA node, in the ventricular myocytes, and in the AV nodes, it has a different effect. I'll tell you what happens in the SA node. When CAMP increases, in the SA node, this CAMP binds with these HCN channels. Now, the CAMP binds with HCN channel, and HCN channel now opens up. So a lot of sodium is released inside the cell. So sodium now is released inside. So again, the negativity changes from minus 60 to minus 40, right? So this changes. So a plus 20 millivolt is added, right, with the help of the sodium that is released from HCN channel inside the cell. So now once the phase, so as you can see, this is the phase 4, which has these funny currents, right? So this CAMP opens up these HCN channels, sodium is released, phase 4 gets steeper. Steeper means it is supposed to be that way, and now this is even steeper because more amount of sodium is released in, right? So the phase 4 gets steeper. It reaches threshold faster. Of course, this was the threshold, right? It reaches threshold faster. And then we have this upstroke right there because of the long calcium channels, right? Long lasting calcium channels. So we have this reaching threshold faster due to camp, increased level of camp, and then we have more impulse, and then we have more, this generation of interest. It's positive chronotrophy, and we have more heartbeat. So sympathetic system induces more heartbeat. It is responsible for more heartbeat. That's one concept. Other concept is in ventricle cells, we have these camps, and then these they increase something which is called as protein kinase A. Now this protein kinase A has two effects, right? The first effect is that it opens these L-type calcium channels in phase 2. Now, as you remember, phase 2 was present in these ventricular cells, right? For the contraction, right? So I hope we can remember that right here. This was the phase 2. That's the plateau. So these are long type calcium channel, and we open that, right? Once we open that, right, we have positive ionotrophy. Now, this is the positive ionotrophy. Ionotrophy means the contractility, the strength of contraction, right? How strong is the contraction? Because this is the time when the contraction is really taking place. Maintains a dipolar state. This plateau maintains a dipolar state, enables contraction, positive ionotrophy, right? So contraction is happening right here at this time. And then when the contraction is done, the cell goes into diastole, right? It goes, relaxes, and that filling is done. And then we have this minus 90, this phase 4, when the cell is waiting for another impulse, right? So increases L-type calcium induces positive ionotrophy. Another thing that increased protein kinase do is that it increases something as called phospholamban. Now, once the phospholamban is increased, we have more calcium uptake in SR. That is this S sarcoplasmic reticulum. It's these stores of calcium, right? So these stores of calcium, they can release calcium and they can take back the calcium. Once they take back the calcium, the contraction stops and the diastole starts, the relaxation starts, and that's how we are able to fill the blood inside our ventricles. So if the calcium uptake in the SR, in the sarcoplasmic reticulum increases, it means the diastole increases. It means it's positively lusotrophic. Lusotrophy is this quantitative way. Lusotrophy means relaxing ability of the ventricles, okay? So quick relax, positive lusotrophy. So in ventricle myocytes, increased level of camps can increase the plateau phase, right? Phase 2, it will increase. It means the contraction, and it will increase this calcium uptake. It will increase this relaxation, okay? So we have more blood now and more contraction. So positive ionotrophy and positive lusotrophy is done via sympathetic system, okay? Another thing in AV node, there's the delay point of the current. What happened here is that increased level of camp, it increase L-type calcium, so L-type increase calcium, right? And we have this phase 0. Do you remember this phase 0? Phase 4, phase 0. In phase 0, we have this calcium rushing in, this L-type, long type calcium rushing in. Once a lot of calcium rushes in, we have this upstroke, right? Right here, the cell jumps from minus 40 to this depolarized state. So imagine if we increase the amount of calcium, the graph will be like that even. So again, in AV node, the L-type increases, phase 0 speed increases. This we call as positive dromotrophy, okay? So what is dromotrophy? It's the conduction velocity, right? Again, if the phase 0, instead of going in a straight line, it will go like that, around like that it will go, okay? Because the amount of calcium is a lot now, so it will go like that. If the amount of calcium was less, it will go like that, right? Because this is the time taken. The time is running in this way. So this is what's going to happen. So in AV node, the sympathetic system will show positive dromotrophy, more speed, right? The conduction time will be more. the fast conduction was going to happen. Okay, so AV node is supposed to stop the current. It will stop less. It will stop the current for less time. Maybe it was stopping the current for 0.1 second. Now it will just stop the current for 0.05 seconds, or even less, or even, I mean, I don't know, it's like that. Okay. What about parasympathetic system? Well, we have this parasympathetic system. It acts via vagus nerves, and this vagus nerves releases something called as acetylcholine. Acetylcholine is a neurotransmitter, and we have these M1, M2, M3, M4, M5 receptors, and M2 receptors, especially they are present on the heart. And once M2 receptors are activated, they are binded with GI, that is G inhibitory proteins. And once they are, they reduce the level of CAMP. Once the CAMP levels are reduced, all of these things, they go in the opposite direction, right? So the HCN activity goes down. We have less number of sodium coming in now. So slower dipolar state, flat phase 4. What I'm saying? So this was the dipolar state, right? Imagine we have more amount of calcium and more amount of sodium coming in. If we have more, the state will go like that. If we have less amount of, it will go flatter like that. Okay, so in parasympathetic system, the direction of the curve, the direction of the graph, it goes like that here. But if it was sympathetic, it will go like that, because the amount of sodium and calcium will be more in sympathetic system, but amount of sodium and calcium in parasympathetic will be less. So that's why the graph goes from here to here. Okay, so that is phase 4, right? There is slower depolarization, flat, so decreased heart rate, negative chromatrophy. What I have written here, crotrophy, okay, it's chronotrophy. Okay, so that was funny currents. That was sympathetic and parasympathetic. I hope I'm able to explain this graph easily, and this is very easy to understand, very, very, very easy. So that was, the whole thing. Let's try to understand conduction system of the heart. We have SA node that is present on the wall right here, SA node on the atrium, and then we have these AV node that's present right here, and then we have bundle of His that we have Purkinje fibers, right? So SA node, dominant pacemaker. It means it can ultimately override this dominant. Okay, I'll try to explain it more easily. So I have written, the text says that it is a dominant pacemaker, right? So let's start, before talking about dominancy, we should talk about dromotrophy. Dromotrophy is the conduction of impulse, right? So dromotrophy is the conduction velocity or conduction of impulse, right? So why SA node is a dominant pacemaker? Let's talk about it. Because, okay, heart has, these potential pacemakers, many potential pacemakers. Even Purkinje fiber can act as a pacemaker in these weird pathological conditions. Okay, so the conduction time from SA node to Purkinje fiber is around 0.22 seconds. It's super fast. So SA node is a primary pacemaker. This is primary. This is secondary. And these Purkinje fibers and bundle of His can be tertiary if the situation are like that. Okay, but SA node controls the rhythm. Okay, because it has the fastest rate of spontaneous depolarization. What is spontaneous depolarization? It is the phase 4, this one. So this is spontaneously happening again and again and again and again and again, and this happens again and again and again and again, and this happens 100 times in 1 minute. And this is the fastest, it's the fastest among both of them, right? So it's happening again and again, and it's happening 100 times in 1 minute, right? So this is why, that's the reason we call SA node as a dominant pacemaker, because it has the fastest rate of spontaneous depolarization. It is the fastest rate of phase 4 happening, that is 100 times, 100 impulses per minute. And this is why this is dominant. And all the other pacemaker like AV node or maybe bundle of His that can become are slow. These others are slower and they get suppressed by SA node rhythm, right? Now, other question is that our resting heart rate is around our resting, it means when we are rested, when we are relaxing, our heart rate is around 72 heartbeats per minute. So SA node fires around 100 per minute, right? But we rarely see 100 BPM at rest, right? Because the vagal tone releases these acetylcholine, that is acetylcholine, right? And again, acetylcholine on M2 receptors, right? M2 muscarinic receptors, that's the full name. So M2 receptors on these SA node, right? And this acetylcholine is released from these vagus nerve, and then this opens these potassium channels, these potassium channels. And once these potassium channels are opened, we have this hyperpolarization again happening. The potassium is leaving the cell again. So hyperpolarization happen, slower depolarization happen. The cell becomes a little more negatively charged than usual. So this is how the vagal tone acts, because it releases acetylcholine on these SA nodal cells and it depresses the cell. It removes a lot of potassium out of the cell. So this is how it happens. That's why your resting heart rate drops from 100 to 70 to 75 BPM. So SA node is constantly held back by a leash of vagal tone. I hope this makes sense. So atropine, let's talk about atropine. So atropine, these are the blocking of brakes. We block the brakes. Atropine is a muscarinic receptor breaker or blocker. Okay, it stops the muscarinic receptors. It blocks the effect of acetylcholine. It removes the parasympathetic inhibition. Now, SA node fires at 100 BPM or even faster under sympathetic influence around 150. So that's why heart rate increases when you give atropine. So atropine is this PNS blocker. Okay. So PNS here, just PNS means parasympathetic nervous system. ANS means autonomic nervous system. I hope you know that. Denervation heart. So heart, when transplanted, it loses its vagus touch. In heart transplant, all autonomic nerves, that is sympathetic and parasympathetic, are removed, are cut. So there is no vagal tone and no sympathetic innervation. So this results in heart rate coming back to its basic 100 BPM, that is pure SA nodal rate, because SA node is present inside the heart, right? So heart rate comes back at 100. So no atropine or vagal stimulation effect happens, so because of no nerves, right? So this is called overdrive suppression. Now, what is overdrive suppression? Overdrive suppression. The key question that we should ask here is that if other pacemakers like AV node and Purkinje fibers can fire automatically, why don't they just take over the SA node? If they are automatic, why they just don't take over SA node? That's a good question. Because of something called as overdrive suppression. The concept of overdrive suppression is that the process by which a faster pacemaker, it's like a statement. The statement says that a faster pacemaker will always suppress the automaticity of a slower pacemaker. This is the concept here. It suppresses the impulse generated by other pacemaker, because SA node is faster in pacemaking, is faster in generation of impulse. It is more positively chronotropic. How it happens? This is a very cool thing. So let's say SA node is firing rapidly, firing fast again and again. Now each impulse depolarizes the other pacemaker cells before they even reach their own threshold. Okay, so number one, when SA node fires, it sends an impulse through the heart, right? This resets the membrane potential of AV node and Purkinje fibers before they can depolarize themselves. So over time, the constant depolarization causes these sodium potassium ATPase pumps or ATPase to become more active in these cells because of the increased intracellular potassiums, right? Not intracellular sodium. I'm so sorry. The pumps hyperpolarizes them further, right? They are even more negative charged. Now it slows their phase 4 slope. Now, as you can remember, phase 4 was this. It slows it, right? So because SA node is firing fast, the pump, they get hyperpolarized. Now it slows the phase 4. They can't reach their threshold of their own. AV node and bundle of phase, they can't reach their own threshold. So their automaticity, they get suppressed. Before they can even reach their threshold RMP, before they can reach their own resting membrane potential, the SA node fires again. And then they have no time to reach their potential, this threshold potential. SA node fires again, you know. So this automaticity gets suppressed. This is called overdrive suppression. I hope I'm able to really explain this concept, because I love this concept. It's like you have a gang member right here, and he's this leader of this gang. It's amazing. When SA node fails, imagine if SA node fails, what will happen? If the SA node stops firing, the overdrive suppression fades off, right? And the next fastest pacemaker will be AV node. So AV node will be the next gang leader. So next fastest member will be AV node, or maybe Purkinje fiber, you know. And then they take over, and then the rhythm is messed up, and then you have arrhythmia, right? So that's how the arrhythmia really happens. So story of this whole overdrive suppression is that SA node is the captain, SA node is the gang leader that keeps all other, you know, these AV, bundle of phase, Purkinje fibers in check. The vagus nerve holds down this gang leader. The vagus nerve holds down this captain, and it holds down, it slows him down. And atropine, right here, atropine, it removes that hand of vagus nerve, and it's like, okay, captain, go ahead. You wanna do something nasty, do it. So atropine is this. I hope we are able to understand how, you know, this amazing concept. Other thing is that AV node right here is the gatekeeper of heart. It delays the impulse of conduction around 0.1 seconds for adequate ventricular relaxation. I hope we already know that. Conduction velocity is around 0.4 millisecond. It's really slow due to less amount of gap junction. How gap junction work? This is two cells. There's a gap, there's a window, so that ions can travel from one cell to another. So that current can travel, right? So if two cells have more amount of gap junction, more amount of ion can travel, more amount of current can, you know, pass. So SA node, they have abundance of these gap junctions, but AV nodes have less amount of gap junctions. That's why AV node is slower pacemaker than SA node. It's all in the gap junction. Let's talk about a bundle of his. This is the bundle of his, and then when it, you know, spreads, we call it Purkinje fibers. Purkinje fibers, they innervates every single ventricle myocardium cells. The functional syncytium. Okay, functional syncytium. What does it mean? Okay, let me read first. Functional syncytium, synchronized contraction, right? It just means that the contraction is synchronized with each other. Okay, it means that if one thing is happening, the other will happen, and the other one happen, and then this is like a synchronized pattern is happening. Without synchrony, the heart would, you know, fibrillate. It will quiver. It will perform fibrillation instead of pumping. The ejection fraction will drop around 0, and the circulation will fail, because it will act like a fish. Have you seen a fish? When we take the fish out of the water, the fish will, you know, fibrillate. You know, it will go like that. It will go haywire, and the ejection fraction is that how much blood is ejected. It will, you know, because a good pumping actually increases the ejection fraction, and fibrillation decreases the ejection fraction, because there is no pumping in this fibrillation. So that's why antiarrhythmic system like AV node delay or Purkinje fiber exists, so that we have time to time this each region perfectly. Okay, the cardiac tissue mass, they behave like these ventricular tissue mass, the cardiac tissue mass of Purkinje fiber, they behave like a single coordinated muscle. Okay, a synchronized contraction is happening. The conduction velocity is super fast, 4 millisecond, 4 meter per second, highest due to increased gap junction at intercalated disc. Now, what is this intercalated disc? I mean, we should know about that. First of all, let's talk a little bit about Purkinje fiber a lot again. Purkinje fibers, these are this terminal part of this cardiac system, right? And they are just modified, changed cardiac muscles. They are not neurons, by the way. Okay, so let's talk a little bit about Purkinje fibers, right? Most importantly, the biggest thing is that these Purkinje fibers are bigger than normal, myocytes, bigger than normal cardiac sites. So this was a normal cardiac cell, and this was a Purkinje, Purkinje cells. They are bigger in size because they wanna, travel. They have more gap junctions, and they wanna have more conduction velocity. So they are larger in, size. Other thing is that they have less myofibrils and more glycogen. They are rich in glycogen, and they are rich in gap junction and intercalated disc. Now, what the hell is intercalated disc, and why do we even have them? What's the function of these intercalated disc? What's the meaning here? So intercalated disc are these junctional complex between two adjacent Purkinje fibers. That's it. They form this end-to-end connection that combine mechanical coupling, electrical coupling together, right? What is mechanical coupling? Mechanical coupling is just desmosomes, and these desmosomes, they anchors the cells together, prevents them from falling apart during contraction. And then we have something called as fascia adherence. Now, fascia adherence, they link the actin filaments to one cell to the next, okay? And then this is the mechanical coupling is happening in this intercalated disc, okay? This disc. And electrical coupling, gap junction, they are low resistant pathways allowing ions to pass, and this is how the electric continuity happens. So intercalated discs are these plugs that mechanically and electrically connect one cell to another. Now, Purkinje cells are filled with these intercalated discs, especially rich in gap junction, because Purkinje fibers are designed for this rapid electric conduction, and intercalated disc contains high amount of gap junctions, and this minimizes any sort of resistance for electricity, and it allows faster conduction speed, right? And this is the reason why we have 4 meter per second speed, unlike 0.3 or 0.5. That is the AV node. So that was the whole concept of intercalated disc and conduction of heart, and SA node, AV node, cardiac action potential. Let's talk about summary. The summary is that the summary of AV node and SA node. So SA node is the conductor, AV node is the musician. I hope we can understand that. It's operating in an orchestra. Sequence of event is that the first step is AV nodes get activated. When AV nodes get activated, the SA node phase 4 starts. When the phase 4 starts, we have this 3 channels opening. First is this transient T calcium, then we have this Na, and then we have potassium. So they come in, both of them, so that positivity increases, and it rushes out so that positivity increases, and then the cell goes from -60 to -40, and then it reaches a threshold at -40. Then the phase 0 starts. When the phase 0 starts, we have these long calcium channels. They open up, a lot of calcium comes in. There's an upstroke, okay? Cell upstroke, it goes to the dipolar state now. The cell is dipolar, and then the phase 3 starts. These are just potassium going out of the cell. The cell is getting repolarized again, right now. So in this way, when the phase 0 ends, when the depolarization ends, the electric wave is generated. Now this electric wave goes and it activates, it depolarizes the atrial depolarization, and contraction of atria happens. Now this is a fast response AP, action potential. Now once the atria depolarizes, right, the AV node receives current. When the AV node receives the current, it delays the current for ventricles to fill the blood from that. The blood was pushed from the atria to the ventricles, right, because atria has now contracted. Once the atria contracted, it pushes the blood to the ventricle, and the current is stopped at the AV node, so that the filling of the ventricles is done well. Once the filling is done, Now the current reaches at bundle of his, right? His bundle, whatever you want to call. So rapid contraction of the ventricles happen. So phase 0 starts, right? Phase 0. I hope you remember that phase 0. This is phase 0. Phase 1, phase 2, the contraction happening right now. Once the contraction happens, the blood, ejection of blood happens. So blood is, removed from the ventricles. Now the contraction happen again, it removes. Now this phase 3 starts. We have this delayed potassium release out of the cell. It relaxes, so phase 0, phase 1, phase 2, phase 3, it happens, like that. Once all of these happen, the ventricular muscle, they get depolarized, and this whole thing happens. And then we have this repolarization, phase 3. I am so tired, honestly. And then we have this whole cycling again, happening and happening and happening again and again. So this was the whole concept of cardiac action potentials.